right, this mini lecture is going to explore the idea of capacitance and capacitors. So another electrical element that we are going to find in our circuit analysis and that we use, whether we know we're using it or not, on a daily basis. So a capacitor is a device that stores charge. You can imagine this is really useful for us, right? We can store charge to then be used later, and that can be a very useful thing. Batteries provide charge for us to run our electronics. So if I can store that charge, then I can run my electronics at a later time. I can tap into it at a later time. So capacitors is really useful for us. We are going to look at a simple representation of a capacitor. They come in a variety of types, but we're going to look at a simple capacitor and analyze it for our purposes, called the parallel plate capacitor. All right, so that's the type of capacitor we are going to focus on in our initial introduction to this. And a parallel plate capacitor is simply constructed with what you might imagine, two parallel plates, and these plates are conductive material, and they are separated by an insulator. All right, so two conductive plates separated by an insulator. Now let's imagine that we take these two conductive plates and we connect them to a voltage source. So here's my two conductive plates connected to a voltage source. What happens? Well, the voltage source, we know, is a source of potential difference. It causes charges to move. And charges begin to move, as we've used conventionally, away from the positive end of the battery or the voltage source. And although they can't pass through this gap, they begin to build up on this plate. It's a conductive surface, and that potential is still felt throughout that entire circuit. Similarly, on this side of the plates, we have a current. The current continues to flow, leaving this side of the plate with an absence of positive charge. Now, we know it's really the electrons moving, so take that out. We've talked about in our previous, or in a later discussion, you'll find that it's the electrons that are flowing here. Or previous discussion, depending on when you're watching these videos. What happens is that the negative side of the battery, the low potential side, ends up being the low potential side of the capacitor. The high potential side ends up being the high potential side of the capacitor. And in the next video, or the video later in the series that you're watching, we're going to look at what happens in that situation. But for now, just want you to recognize that a capacitor has this ability to store charge when a potential difference is put across it. The side of the potential that is at higher becomes the high side of the capacitor plate because charge is moving towards that plate. The low side, the low potential side of the battery becomes the low potential side of the capacitor because charge is moving away from that plate. All right, when we think about positive charge moving. Okay. In a circuit, a capacitor actually is represented exactly how we might think about a parallel plate. So two lines, so in a circuit, the capacitor is represented by two parallel lines of even length. Okay, so two parallel lines of even length are how we represent a capacitor in a circuit. Okay, so if the capacitor is the device that stores charge, how much charge can it store? Well, what might that be dependent on? And you might imagine that based on sort of your learning and your thought process in terms of potential and potential difference, that if I make this potential difference larger, I know that I get more charge to flow. If I get more charge to flow, then I probably am going to get more charge stored on the capacitor, and you would be thinking correctly. So if we increase the potential difference, the voltage that we apply across the capacitor, we increase the charge that that capacitor can hold. And we find that that relationship, that direct relationship holds true, and the charge on a capacitor is equal to the voltage times what's known as the capacitance. So the constant of proportionality for this relationship is what's known as the capacitance. So C is the capacitance. Now the capacitance is not dependent on the charge or the voltage, okay? The capacitance is a property of the capacitor itself. So what might it depend on? Well, it depends on things like size and shape, depends on the separation distance. I think I just spelled that wrong. Separation distance. And it can even depend on the material itself. Okay, so it even depends on the material itself. Okay, so why might that make sense? Well, let's imagine we're looking at size, and I have a small capacitor versus something that's large, lots of conductive surface. A lot of conductive surface has the potential to hold a lot of charge, right? So for example, if I increase the area, we might expect the capacitance to go up, okay? So giving you a kind of a framing of what would influence capacitance. Now for many shaped capacitors, this is an experimental value. But the capacitor that we're going to be playing with, the parallel plate capacitor, its geometry allows us to actually calculate the capacitance for a parallel plate capacitor. So we're going to get to that in just a minute. Now, let's look at the unit of capacitors before we do that. So we know that the unit for charge is coulomb. The unit of voltage, of course, is the volt. So the unit for a capacitor, for capacitance, has to be coulombs per volt. That will give us coulombs in our unit analysis, if we do a unit analysis of this relationship. Well, a coulombs per volt goes by what's known as a farad. We use the capital letter F to determine for our unit symbol. All right, so capacitance stores charge. That charge is related to the voltage applied across that capacitor times the capacitance. We talked a little bit about why that would look like that. The capacitance is a property of the capacitor itself related to things like size, shape, separation distance. We're going to analyze that for a parallel plate capacitor. The unit of capacitance is a farad. All right. One of the things that we can utilize when we look at the capacitance for a parallel plate capacitor is that we're going to pull back some information that we learned from our discussion of voltages, potential difference, and electric field. So if it's been a while since you've looked at that video, go back and check that out. But we know from, and we evolved from our discussion there, that if I have two plates that are very large relative to their separation distance, so that the separation distance is much, much smaller than the plate. So if we think about that as kind of the area of the plate, so much, much smaller than the plates, that the electric field produced between those plates is uniform. Okay? And when we go back and we look at the relationship between charge and electric fields and voltages, we can find and determine that the capacitance for a parallel plate capacitor is equal to epsilon naught, the permivicity, oh my gosh, I cannot say that word today, epsilon naught times the area over the separation distance. So this is for a parallel plate. This is going to be the relationship we can use to determine the parallel plate capacitance in our problem solving, okay? So the geometry, and if we integrate this potential across the space, we look at the charge and all the E-field relationships, this is what we end up with for our capacitance. So we're going to use that moving forward. All right, let's do an example that allows us to sort of play with these new equations and ideas that you have just been introduced to. So as I erase, I'll quickly review. So capacitors, again, are devices that store charge. Well, we stick them in a circuit, which check out the RC circuit, a little mini lecture. They do some really fun things. We rely a lot on them. The amount of charge that they can store is dependent on the capacitance and the voltage that's applied. And then we can have a relationship. We know a relationship for the capacitance, which is a property of the capacitor, for a parallel plate capacitor. All right. So let's look at an example. I'm just going to pop one up. Let's just play with these equations. So we're going to calculate the, oops, let's get rid of the extra words there. Calculate the capacitance of a parallel plate capacitor whose dimensions are 30 centimeters by 20 centimeters by 3 centimeters and are separated by an air gap, which is the insulator, of 1 millimeter. We want to know what the charge on each plate is if we apply a 12-volt source to that capacitor. Right, so what's the charge if we apply a 12-volt source? So we're going to start where the physics is asking us. So the charge, remember, on a capacitor is equal to the capacitance times the voltage. So I'm given that the voltage is equal to 12 volts. I do not know what the capacitance is. So I'm left with the charge is equal to 12 times C. So we need C. Because we're using a parallel plate capacitor, we are going to look at the capacitance relationship that we know for a parallel plate, which is epsilon naught times the area divided by that separation distance. The area of our parallel plate capacitor is going to be 0.2 meters, so 20 centimeters, times length times width, 0.03 or 3 centimeters, which is 6 times 10 to the minus 3 meters squared. So that's our area. And our separation distance is given as 0.001 meters, so 1 millimeter. So we're going to use that in our equation. Epsilon naught is a constant, which is 8.85 times 10 to the minus 12. You do not have to memorize those. 6 times 10 to the minus 3 divided by 1 times 10 to the minus 3. And we get our capacitance equal to 53 times 10 to the minus 6 farads, which we often put capacitance into microfarads, okay? So 53 times 10 to the minus 6 farads, we can now use that up there, and we find that our charge on the capacitor is 12 times 53 times 10 to the minus 6, and the charge on that capacitor is 6.4 times 10 to the minus 10th coulombs. All right, so just using those equations, pretty straightforward equations. The idea, of course, is what's important in terms of why the capacitance might be dependent on area. It can hold more stuff, right? Why is the charge dependent on the voltage? More potential. But where it really gets fun is when we look at circuits and how capacitors look in circuits. So we'll go ahead and do that video next. Nice job.